Welcome to the Explainer. So, you're building with AI. It can feel like you're lost in a maze, right? You've got this awesome demo, but how do you turn that into something real, something reliable? Well, today, we're unpacking the blueprint that's got the answers. We're diving into Chip Huyen's incredible guide, AI Engineering. Okay, so how are we going to tackle this? We're going to follow a really clear 6-step journey. We'll start right at the heart of it all, the AI model. Then we'll move step by step through quality checks, how to actually shape its behavior, what to feed it, how to make it fast and efficient, and finally, how to put the whole thing together into a real system that actually works. Let's get started. All right, first things first, our journey starts at the very core of any modern AI app. Before we can even think about building, we have to understand the engine that makes everything run, and that's the foundation model. So, what exactly is a foundation model? Well, it's not built for just one specific job. The best way to think about it is it's less like a tiny specialized screwdriver and more like a massive general purpose engine. The whole point is you don't have to build a new engine for every single project. You just adapt this one core engine. And that, right there, is a huge change from the old days when you literally had to start from scratch for every new task. Okay, so if we pop the hood on one of these models, what do we see? Really, there are three main parts. First, there's the mountains of training data it learned from. That's its knowledge base. Second, you've got its internal structure, its architecture, which, let's be real, is almost always the game-changing transformer design these days. And then third, and this part is so important, there's a post-training phase. This is where the magic happens, where the raw model is taught to be helpful, safe, and actually follow our instructions. It's what turns a giant brain into a useful assistant. Now, here's something you absolutely have to get your head around. These models are probabilistic, not deterministic. What does that mean? Well, a calculator is deterministic. 2 plus 2 is always 4. But with AI, you can ask the same question twice and get two slightly different but still perfectly good answers. And that's not a bug. It's actually a feature. It's where its creativity comes from. But if you're an engineer, that means you have to design your systems to work with that randomness, maybe even use it to your advantage. So wait a second. If the model's output isn't always the same, that brings up a really big question, right? For anyone trying to build something with this, how do you know if it's any good? How do you measure quality when there isn't just one right answer? You've got this super powerful creative engine, but how do you check its work? And that puzzle leads us straight to our second step. It's an old saying, but it's totally true. You can't improve what you can't measure. And honestly, in AI development, just figuring out how to measure performance can be the single biggest hurdle you'll face. I'm not kidding, it's not just important, it can often be the absolute hardest part of the entire project. And the reason it's so tough is that we're not just looking for a simple right or wrong answer, like a math problem. We have to judge all these subtle qualities, like, is the summary it wrote factually correct? Is the tone friendly but not too informal? Did it actually follow all three parts of my really specific instruction? The old metrics like simple accuracy just completely fall apart here. This whole evaluation thing naturally leads to one of the first giant decisions every team has to make, the classic build versus buy choice. So, do you buy access through an API from a big company? I mean, you're basically renting their super powerful model. It's quick to get started for sure, but you give up some control, and you have to send your data to them. Or do you build by taking an open source model and hosting it yourself? That's a ton of engineering work up front, but you get complete control and all your data stays in-house. And listen, there's no single right answer here. It's all about weighing these trade-offs. Okay, so you've picked a model and you've figured out how to measure if it's doing a good job. Now the real fun begins. This is where we get to actually shape the model's behavior and really dial it in for our specific needs. The book gives us this awesome, clear ladder of techniques. You start at the bottom rung, which is the easiest and cheapest, and you only climb up when you have to. So you always start with prompt engineering. That's just giving the model good instructions. If that doesn't quite get you there, you can move up to something called RAG, which is a way to give the model access to external documents and knowledge. And then, for the most control, the top of the ladder is fine-tuning, where you're actually changing the model's internal wiring with new data. The key is to climb this ladder one step at a time. And when it comes to those two big guns, RAG and fine-tuning, the book has this fantastic rule of thumb. It's so simple. You use RAG to fix knowledge problems. So if the model doesn't know about your company's brand new product, you give it the product docs to read. Easy. but you use fine-tuning to fix behavior problems. If you need the model to always answer in a perfect JSON format, you fine-tune it to teach it that new skill. Knowledge versus behavior. It's a great way to think about it.
But here's the thing. Whether you're doing RAG or you're fine-tuning or anything in between, all of it depends on one single critical resource, and that's data.
This quote really gets to the heart of a huge shift happening right now. Look, the big, powerful models, they're becoming widely available, almost a commodity. So the thing that's going to make you stand out isn't which model you pick. No, the real differentiator, the thing that gives you an edge, is your unique, high-quality data. That data becomes your secret weapon. Okay, but let's talk about a classic problem, a real gut punch for a lot of AI projects. Let's say you have a fantastic model, it's got great data, the answers are amazing, but it's super slow, and it costs a ton of money to run every time someone uses it. That's not a real product, right? It's just a cool but expensive demo. And that very practical, very real challenge brings us to our next stage. So yeah, let's talk about making things fast and cheap. This gets us into the world of inference optimization. It sounds like a complicated term, but really it's just all the smart engineering tricks you need to make your AI app actually run fast enough and cheap enough to be used in the real world. And you can attack this problem on two fronts. First, you can optimize the model itself. There's a technique called quantization, which is kind of like compressing a giant photo. You make the model smaller and faster, but you don't lose much of the quality. Then second, you can optimize the whole system that serves the model. For example, batching requests is a great trick. It's like waiting for a bus to fill up before it leaves the station. It's way more efficient to handle a bunch of user queries all at once instead of one at a time. Yeah, these are technical details, but they are absolutely what separates a toy from a tool that can scale to millions of users. Okay, let's take a breath. We've talked about the model, how to measure it, how to shape it, the data it needs, and how to make it run fast. We've got all the pieces laid out on the table. Now it's time to put it all together and build the final machine. And here it is, the complete blueprint. What you realize is that a real-world AI system isn't just one model call. Oh no, it's an entire system, like a little factory. You've got safety guardrails checking what goes in and what comes out. You've got a smart router that knows, hey, this is an easy question, send it to the cheap model, or, ooh, this is a hard one, we need the big brain. It's got a cache to member common answers, so it's super fast. And maybe most important of all, it has a feedback loop, so it's always learning and getting better. This whole setup, this is what turns a cool but fragile demo into a rock-solid application. And that, right there, is really the soul of AI engineering. It's not about a collection of clever hacks or tricks. It's about having a system, a blueprint, a repeatable process that lets you take the incredible, raw potential of these models and turn it into something real, something reliable, something valuable. This is the framework. This is how you build the future, and you can start today.